Titration in Chem 1 was strong acid, strong base, if I remember right. I think so, yeah. I'm pretty sure. But all an acid-base reaction is you take an acid and a base, and you have one-way reaction arrow, and it goes to form products. And there are 4 possibilities, and we'll talk about each one of them. It could be that you have a strong acid and a strong base, a little different chemistry, then a weak acid, a strong base, a strong acid, a weak base, and the 4th one is weak both. Weak acid, weak base. So different chemistry going on with each one of these, but they have some things in common. So one of the things that they'll have in common is that on either side of the reaction arrow you can pick out 2 sets of conjugate acid-base pairs. And you kind of had some work with that. And here are examples of conjugate acid-base pairs. They differ by a proton. Differ by a proton. So let's start with the first titration you guys are going to do tomorrow is strong acid, strong base. I'm pretty sure it's HCl is your strong acid and NaOH is your strong base. Now, one of y'all stopped the other day and we kind of talked about even though it's a strong acid, it doesn't mean that the solution is over the top acidic. Because a strong acid means that it breaks apart entirely. But if its molarity is low, it's just going to be a mildly acidic solution. Does that make sense? Yeah. So here is the chemistry that's going on. They basically switch partners. You end up with, we're going to call NaCl the salt. Actually, I have a term coming up for that. This is a neutralization reaction. This is our salt, and this is our, of course, water. So we could find the pairs that differ by a proton. The chloride ion always throws me off. So our HCl differs from our chloride ion by a proton. Our OH differs by our H2O by a proton. I buy that. Sneeze. Net ionic equation, we remove the spectator ions, or spectator ion, excuse me, only the chloride, or the sodium ion, and the chloride ion. An example of a weak acid and a strong base. So, we've spent some time talking about this and doing some homework. So hopefully you're kind of getting an idea of this is a weak acid. On your test and in homework, you always have available to you the Ka tables. So if you find a Ka for that, that's a weak acid. And NaOH, strong base. This is your salt over here. Conjugate acid-base pairs, they differ by a proton. I buy that. Your acetic acid, your acetate ion, your hydroxide ion, and water. Net ionic equation, the same thing as the regular equation without the sodium ion. An example of a strong acid, weak base. Here we go. Strong acid, hydrochloric acid. Oops, sorry. Put SA under HCl. NH3, weak base. Form salt right here. Conjugate acid-base pairs look like this, differ by a proton. And the net ionic equation looks like this, minus the chloride ion. Last but not least, or maybe least, because if they're both weak, the chemistry gets not quite so obvious. If you think the chemistry is complicated with your weak acid, strong base, or strong acid, weak base, the chemistry with both weak is very interesting. So acetic acid and ammonia, examples we had before, both weak. weak acid and weak base respectively. Conjugate acid-base pairs, and the net ionic equation doesn't have anything taken out. So that's kind of the background of it. That's kind of the bird's eye view. Well, hopefully this will start to kind of, well, maybe not. Oh, okay, sorry, I forgot there's one. I was going to say ring some bells, but hold that thought. So any acid-base reaction can be thought of stepwise, where the acid ionizes, kicks off a hydrogen. The base absconds onto a hydrogen. So the kicking off of the hydrogen is the Ka of the acid. The absconding onto a hydrogen is the Kb of the base. And then the neutralization step. Just think, what does protonation of hydroxide ion mean? Protonation, think H+. Protonation means adding H+. Adding H+. Protonation of hydroxide. So wow, H+ plus OH- gives you water. Okay, so that's the making water step. So if we're making water, does this make sense? That it is the opposite of destroying water. I know, don't mean to be dramatic about that, but we said that actually water auto-ionizes to do this, H+ plus OH-. And we said we could write a K expression, and we're going to call that KW, is equal to H+ OH-. Okay, is that okay? So that is the deprotonation of water. The protonation of water is 1 over. If you reverse it, if we reverse this, which is what we're doing here, that is times -1. And if you reverse it, what do? You take the inverse of the KW. All right, so then we said if you can stepwise describe an overall reaction of interest, then we can take those, our equilibrium of interest, we can take all of them and multiply them by each other to get the overall K. So the K of this reaction is K1 times K2 times K3, the ionization, the hydrolysis, and the protonation, which is Ka Kb over Kw, which what's Ka times Kb? Kw. Okay, so that goes. So in general, if the Ka of your ionization or the Kb of your hydrolysis, your absconding onto a proton, is relatively large, it will go in the forward direction. Okay. Now on to, well, I guess not quite. Keep trying to get ahead of myself. Well, let's consider this. What if we have equal moles of a strong acid and a strong base? Oh, you're fine. Hopefully this will help for the first. So a minute ago, the strong acid we used was HCl. The strong base we used was NaOH. Oops, let me put this above. Goes to form salt, which in this case NaCl plus H2O. What if we have the same moles of this? So let's just say we had 0.5 moles and 0.5 moles. Okay, so when the dust finally settles, we're going to get, the stoichiometry is 1 to 1 to 1 to 1. We're going to get what? 0.5 moles of this, 0.5 moles of this. And this is entirely going to be gone. All right, so now you have this swimming around as your product. No acid-base chemistry going on there. And actually that's kind of what we've been talking about. Of course, your NaCl is going to ionize, Na+, Cl-. You're like, dude, I don't think that your Na plus is going to, let's see. I don't think your NH plus is going to absorb a hydroxide ion. Right? Your chloride ion is not going to combine with hydronium or hydrogen ion. This is going uphill. Okay? So that's to say this solution that you make with equal molar quantities of a strong acid, strong base, neutral, totally neutral. And you might be like, well, shouldn't all situations be totally neutral? No. Let's switch it up a little bit. That's scenario 1. Scenario 2, let's see, what was our weak acid? Was acetic acid, CH3COOH, plus a strong base, NaOH. Okay, goes to form, we said, sodium acetate, NaCH3COO minus, and water. Okay, cool. Well, let's just say we have 0.5 moles. We're going with easy stoichiometry here. You'd be like, wow, that's pretty cool. This is all gone. Okay, and what's left is this over here. Now, we do have a little bit of acid-base chemistry going on. Sodium acetate. Take this, know that it's swimming around as Na plus and CH3COO minus. Right. So here's where this actually is what I would call the conjugate base of a weak acid. So that little culprit, that little ion, polyatomic anion in there, is actually going to abscond. It's going to act as a weak base. It's going to abscond onto a hydrogen. It's going to be an equilibrium of a water molecule and form, this is what we did for the day. No, I got it. You sit. And form the hydroxide ion. CH3COOH, that's the conjugate acid, plus OH minus. This thing is basic, direct. Depends if you want a basic solution or not. Okay, so the neutralized, when at neutralization, okay, the thing's basic. Why is it basic? It's basic because of the formation of that. Okay. All right. Gonna think through this one too. What the heck? We did those other ones. I don't have the fourth one because, like I said, the whole weak acid, weak base thing is something that's no fun. So let's go on to this third scenario, which we used ammonium as our weak base, HCl plus NH3. So here's our strong acid, weak base, one-way arrow, forms NH4 plus and Cl minus. And we're just going to go with 0.5 moles. You see where I'm going with this? Okay, so with equivalent equal moles of your strong acid weak base, okay, what you have driving of the pH of your solution is the presence of your conjugate acid of a weak base. Okay, so of course what that's going to do is be in equilibrium, with that. So the darn thing's going to be acidic. That's my bottom line, okay? It just is. So equal molar quantities of a weak acid and weak base, I guess it wouldn't be that difficult. You just need to track down the chemistry that's going on. But it's not obvious whether it will be acidic or basic. It depends upon the strength of your weak acid and your weak base. Okay. Cool. Now, yeah, so this is where I say basically 1, 2, and 3, yes. 4, no. Okay. All right. So this is where I started to say, I hope these ring some bells. These terms ring some bells. Basically, no pun intended. Make sure we're all kind of on the same page. I'll draw it right here. You guys, tomorrow's lab, you're going to get the burettes out. We'll talk about the whole stopcock thing. And I think you guys are going to, you can't use Erlenmeyer flasks. You're going to have to use beakers. Because basically, instead of doing it colorimetrically like you did before, you guys are going to have pH probes in there. And you need room to put the pH probe in there. So you have beakers. And I'll have stir bars. I guess there was a casualty yesterday at the West Burlington campus. It's okay. One of the pH probes, I told you about that kind of glass ball down there, the semi-permeable membrane. It's pretty thin, so it got whacked by the stir bar. So the student came up and said, it's not working. And so, Carl chased down. He's like, well, do you have, and this is supposed to be NaOH, okay? And do you have HCl there? And like, yeah. It worked before, but anyway. So in tomorrow's lab, the stuff in here is going to be NaOH, and it's going to be your titrant. That's the term we use for that liquid. And remember, we drip it in. And last time you looked for a color change, but this time you're going to look for a pH change. And this is your analyte. Okay, cool. So for this reaction, this reaction is that first one I wrote up there. So you're going to drip, drip, drip in your HCl. At some point, you're going to use up all of your HCl. Excuse me. At some point, you're going to use up, all of your HCl. You're going to drip in your NaOH. You're going to drip, drip, drip your NaOH. At some point, you're going to use up all of your HCl. And we call that the equivalence point. Okay? And that's what you're going to be after. Kind of. So that's kind of the deal. Yeah, I got 47. We're okay. Thanks for pointing that out. I got 2-ish minutes. Because what I don't cover here, I got to kind of do a little bit more for pre-lab. But I'll have to decide how much I want to do for pre-lab, how much to say, just wait until Friday's lecture. So we'll just see. But before we... Well, I want to get to this next part. The chemistry is going to be different at each one of these regions. So the equivalence point was the only point you guys were cared about in Chem 1. Now actually we're going to look at the chemistry before the equivalence point, at the equivalence point, and after the equivalence point. So your titration's a little more interesting. And you're going to be monitoring pH as you drip in NaOH titrant. Yeah, that's good information. So this is a curve. It's called a pH titration curve, and you will be getting 2 of these tomorrow because you're going to run strong acid, strong base, and then a weak acid, strong base. So the way this works is along the x-axis actually is volume of titrant. So you're going to be dripping in NaOH, so that's volume of NaOH. You're going to have the pH probe in here measuring the pH. So start out with, you have only HCl, an aliquot of HCl. So not so surprising, okay, the pH along the y-axis is very low, very acidic, okay. Characteristic, can you kind of see the S here? Okay, hopefully you can kind of see an S. It goes up and over. This characteristic S-curve is actually what your pH will, changes that your pH will go through in a strong acid, strong base titration. This steep change right here, inflection, that is your neutralization point. That is the tipping point when all of the HCl you have in here has been, or is the crust being consumed by your NaOH. So on the other side of that curve, check it out. After you, looks like about a volume between 25 and 30 mils. Okay, look how it kind of straightens out into just a pure, okay, very basic. Why? Well, because all of your HCl is used up, and what's driving the pH? Basically that NaOH you're dripping in, okay? So, yeah, we'll talk more about that tomorrow. I'm kind of leaning towards just talking you through nuts and bolts and then talking about the chemistry on Friday.